we're going to take our discussion of precipitation reactions a step further. Up until this point, we've been focused on writing what's known as complete molecular equations. And we're going to abbreviate this CME. So the CMEs should never have charges or ions. Yes, we have to break down the compounds into their ions to do-si-do them and figure out what the products are. However, at the end of the day, your final presentation of a CME should be a balanced equation with states and no charges. The next thing we're going to put together is known as a complete ionic equation. We're going to do CIE for that one. The CIE is honestly the most accurate illustration of what's going on in the beaker. So everything that's aqueous is going to be broken down into ions in our complete ionic equations. If it's a solid, if it's a gas, if it's a liquid, we keep those things together because that's how they actually exist. When a solid forms, the cation and anion that make up the solid are actually bonded together. The other things, the aqueous things, they're single, they're ready to mingle, so they're just floating around. Last one is going to be the net ionic equation. While I love the complete ionic equation because it helps me visualize what's going on in that reaction mixture, sometimes all the details, all those spectator ions, and I'll talk about that in a minute, just kind of muddy the picture. And so the net ionic equation just focuses on how we got to the precipitate. And we're going to eliminate all the spectator ions. They're kind of boring. They didn't do anything. They didn't change. So this is the cleanest, neatest picture of the actual reaction. Let's start by breaking down these compounds into their respective ions. So for lithium sulfate, I know that lithium is in group 1 and it's going to have a +1 charge. I'm not going to bring down the 2 because the 2 belongs to sulfate. That's the charge on the sulfate. Here, similar thing going on. This 2 doesn't belong to the acetate. That helps me figure out that one of my ions is a Pb2+, kind of doing like a reverse crisscross there. And then the other ion is acetate. And by memorizing my polyatomic ions, I know that that has a -1 charge. So we're gonna do-si-do these. We're gonna have lithium combined with the acetate and lead combined with the sulfate. And when I do that, and we need to make sure, I'm going to do all my scrap work up top here, and then I'm going to write my final answers for the CME and the CIE and the NIE. Let's focus on the scrap work then. So first thing I would do, I do Li plus and C2H3O2 minus, and I'm noticing that they have a +1 and a -1 charge. That means that they're going to combine in a 1-to-1 ratio. The other thing I'm noticing is that both of these ions, if I look at my solubility rules, we have a group 1 ion, we have acetates. Those things are always soluble, no exceptions. So because it's always soluble, I can label this as aqueous. And I'm going to do something similar for my other 2 ions. I'm going to start with lead though. Always start with the positive ion first. So I got Pb2+ with SO42-, and we got a +2 and a -2. So I can crisscross it down and reduce, or I can skip that step thinking because the charges are the same, +2, -2, they're going to combine in that 1-to-1 ratio again. Looking at the solubility rules, things containing lead are notoriously insoluble. So this is going to be my precipitate. This is going to be the solid that forms in the reaction mixture. All right, now that we have all the work done, and again, this isn't any of my answers, this is just a bunch of gibberish, a bunch of scrap work. Now I can start putting together my different types of equations. So I'm going to start with the CME, complete molecular equation. This part is going to be a copy job. Leave a little bit of space for coefficients. We got to balance too, right? It doesn't matter what order you write your products in. Alright, so I have everything written down. Very important, before you go to the next step, balance the reaction. We have 2 lithiums over here and just 1 lithium here. So I'm going to want to put a 2 out front of the lithium acetate product. That also gives me 2 acetates, which makes sense because I have 2 acetates right there. Lead and sulfate, I have 1 of each on both sides. Alright, so we're good with the CME. Next one will be our complete ionic equation, our CIE. The tricky part about the CIE is the distribution of the subscripts and the coefficients, in my opinion. So the first thing to know about the CIE, if it's aqueous, that means it's soluble, and that means in the reaction mixture, in that water, the ions are separate. So that's what we're trying to show here. So instead of writing this all together like this, I'm going to take this 2 because there's 2 lithiums per every 1 sulfate. So I'm going to write that there's 2 Li pluses, and the states have to go after each one of these. So 2 Li plus, and then I have 1 sulfate, do a plus in between, and that's also going to be aqueous. Lead, there's 1 lead, and it's aqueous, so it's going to exist as an ion. Now, there's a subscript of 2 next to the acetate ion. We don't want to keep it as a subscript because keeping it as a subscript would imply that the 2 acetate ions are somehow connected to one another, which they aren't. So we just want to illustrate the ratio, so we're going to move the 2 out front. So subscripts that come from crisscrosses, when you're writing your complete ionic equations, need to turn into the coefficients of the balanced reaction. So let me circle some of those. So here we had a subscript that came from a crisscross, and that turns into a coefficient. This is another subscript that came from a crisscross. It's going to turn into a coefficient. Alrighty, on our next one, the lithium acetate. It's aqueous, so I want to separate it into its ions, and there's a 2 out front. So that means I actually have to distribute this coefficient to both of my ions. I'm going to write them separately, but there's going to be 2 of each. And paying careful attention to all this really does pay off, because you'll have a balanced complete ionic equation when you're through. Otherwise, you got to go back and balance each one individually. That takes a bunch of time. So paying attention at the start is really helpful. I feel like I'm going to run out of room, so I'm going to write my products down here. So I'm going to do 2 Li plus, and that's still aqueous, and 2 of the acetates, also aqueous. Good news, solids do not separate. I think of those as the couple that fell in love and they're annoyingly like clean, right? So keep them together in all forms of the equations. Just rewrite it. So the next thing we need to identify are spectator ions. Back to my club analogy. I don't know if I've told you this before, but in my mind, and I was kind of excited that I knew that I had a lecture about this morning, the equations represent what's going on in the club, right? So lithium sulfate came together, and they just drove there together. Same thing with lead acetate. And so once they got into the club, they all went their separate ways. And that's what we see here. Lithium is a single ion, sulfate's a single ion. They're all floating around. They're not hooked up with anybody else, right? And then, there was like a love connection, right? Because then lead and sulfate found each other and fell in love, and now they're a couple. So why I go into this analogy, why it works so well, is because then we have the spectators. Those are the ions that came to the club. Maybe they danced a little bit, but at the end of the day, they just watched everybody else fall in love. Nothing changed about them. They came single and they left single. So they need to look, spectator ions need to look exactly the same on both sides of our equation. Now, I don't want to cross out my spectator ions in my complete ionic equation. The word complete, right, we need to show everything, including the spectators. So I'm just going to put like maybe a little dot underneath them to kind of point them out. And then I'll rewrite my net ionic equation without the spectators. So lithium. Lithium is a +1 over here and a +1 over here. So spectator, didn't change forms, didn't hook up. Sulfate made a love connection. So sulfate doesn't count as a spectator. Same thing with lead. They look different on the different sides of the equation. Acetate, however, is acetate ion over here and acetate ion over there. So our spectators for this example will be lithium and acetate, since they didn't change forms on both sides of the equations. That leaves us with our net ionic equation. We're leaving out the spectators. So we have sulfate, we have lead, and they hooked up to form lead sulfate. I didn't really emphasize it because all of the coefficients were 1, but I was paying attention to coefficients, kind of balancing it in my head. So if you had to bring down lithium, we're not because it's a spectator, but you would also bring down this too. In this case, I brought down 1s, and now it's balanced in the final form because I brought down the 1s. Alrighty, we're gonna practice this. This is challenging, so hang in there, keep on practicing. We're gonna go through more examples together, but it could be a lot of fun once you get the hang of it. It just brings in a lot of different topics. Here we have aqueous silver nitrate solution being combined with an aqueous sodium sulfate solution. Let's go ahead and predict the products. So the silver nitrate is going to break into silver, which has a +1 charge, and nitrate, which has a -1 charge. Our sodium sulfate, this too belongs to the sulfate. So when I write my sodium ion, remember it's a group 1 ion, and it's not a weird one like mercury. It's not a diatomic ion. So it should just say Na+. We're gonna recombine these. Let's do-si-do them. So silver with sulfate and sodium and nitrate together. So again, this is just all scrap work over here. I always take my time and check my crisscrosses. Don't skip steps. So this 2 is going to come down and become a subscript. So we're going to have Ag2, and then the +1 is not going to matter. So we'll just write SO4. Silver, anything with silver, lead, mercury, it's typically insoluble. There's a couple of exceptions, like when we're working in the lab and I need silver ion, I typically head for silver nitrate. This is the one that I've had the most success with getting to dissolve. But everything else with silver, it's super hard to get any of it to dissolve. So we're going to do silver sulfate as a solid. And then the other combination is a +1 and a -1. So I know they're going to combine in a 1-to-1 ratio. We just have to make sure to write our cation first. We get sodium nitrate, which because it has that group 1 cation, this is going to be aqueous. Put together our different equations here. So I'm going to start with my complete molecular equation. The beginning part is a copy job. Just leave room for coefficients. When you're writing these down, also make sure you're remembering to include the states. It's a lot of writing, so it's easy to forget something. And then on the product side, we got this solid silver sulfate that forms, and sodium nitrate, which will be aqueous. Balance it. I have 2 sodiums, so I'll put a 2 out front over there. That gives me 2 nitrates. I only have 1 nitrate over here, so let me put a 2 out front here. That gives me 2 silvers, but I'm okay with that. And then 1 sulfur on each side. So that's balanced now. Moving on to my complete ionic equation. We need to distribute. So this 2 will get distributed to both of these ions. And I'm going to write them as ions because they're aqueous. That means they came together, right? But they're not a couple. So right away when they went inside, they went their separate ways. Right away when you put silver nitrate into water, it's going to break apart, dissociate. So we're going to have 2 Ag pluses, and we'll label that as aqueous, and 2 nitrates, also aqueous. Remember the rule from last time. If the subscript came from a crisscross, as did this too. If the subscript comes from a crisscross, that becomes the coefficient in your complete ionic equation. So there's 2 sodium ions per every 1 sulfate ion. So far so good? All right, so over here, we'll keep the solid together. That's the precipitate. And we would see that like accumulating on the bottom of the beaker. Or maybe it would get like super cloudy, something like that. And then we have a coefficient that needs to be distributed to the respective ions. Right, 2 Na plus aqueous and 2 nitrates, which are aqueous. Quick check, make sure it's balanced. And then while you're doing that, start thinking about who are the spectator ions. Which species look exactly the same on both sides. And so I'm looking at nitrate. Looks exactly the same on both sides, as well as the sodium. And the other thing, as you're crossing stuff out, this comes into play in more advanced balancing that we're going to get into when we balance redox reactions. But the coefficients have to be the same to cancel them out completely. So the fact that this is 2 nitrates and this is 2 nitrates works out in our favor. It gets a little bit trickier when they have different coefficients. But for now, you'll see the same coefficients and you'll be able to cancel out the spectators. Our last version then is our net ionic equation. That's going to show the ions that went to form our precipitate. So the 2 silver ions combined with 1 sulfate ion to form the solid silver sulfate. Aqueous ammonium carbonate combines with aqueous calcium chloride. This 2 belongs to the carbonate. And here we have ammonium, which has a +1 charge. Calcium's in group 2A, so it's going to have a +2 charge. The 2 that I see here, it's not going to be diatomic chlorine, that's a gas. The 2 goes back to the calcium, and I want to think of this as being chloride ion, which is a monoatomic ion. Ammonium with chloride, and then we'll combine the calcium and the carbonate. So +1 -1, that'll give us NH4Cl. Any compound that contains an ammonium ion is going to be aqueous. And I'll reorder those. So first I have Ca2+, and then next I should write the carbonate, CO3 2-, +2 -2, that's going to be a 1-to-1. That gives me calcium carbonate, which, looking at the solubility rule all the way towards the bottom, that'll most likely be a solid. Starting with my complete molecular equation, the order of the products doesn't matter, just and my precipitate, the solid calcium carbonate. Alright, balance it. So we have 2 ammoniums. That'll mean putting a 2 in front of the ammonium chloride on the product side. That gives me 2 chlorides, that's fine. 1 calcium on both sides and 1 carbonate on both sides. So for the complete ionic equation, I'm going to write all of the aqueous compounds as ions. This 2 means that there's 2 ammoniums per every 1 carbonate. So that belongs out front. It's not part of the polyatomic ion. It came from a crisscross. Carbonates, just 1 of them, aqueous. one calcium ion. There were 2 chloride ions per every 1 calcium ion. So that subscript then becomes a coefficient. This 2 here needs to be distributed to both of the ions when I break it up. So I'm going to have 2 ammonium ions, 2 chloride ions, and my solid. Always double check that everything's balanced, and then you can go ahead and write your net ionic equation. So who are the spectators here? Looks like ammonium and chloride are the species that didn't do anything. They didn't react, they didn't change forms, none of that. So I'm going to rewrite everything else. We had carbonate, calcium, forming the solid calcium carbonate. In this particular problem, we're given written names for the 2 reagents. Our first step then will be to establish the formulas that correspond to these written names. I'll start with the potassium. That's in group 1, so I know it's going to have a +1 charge. Carbonate is a polyatomic ion. It has a -2 charge. Lead is a transition metal, but we're told that it's lead 2, so I'll do Pb2+, and then we have nitrate, NO3-. First thing will be to write the reagents as formulas. So I'm going to crisscross K+ and CO3 2-. That gives me K2CO3, and it has a group 1 cation in it, the potassium, so it's going to be aqueous. Pb2+, I would have to put parentheses around the nitrate and bring the 2 to the outside. So I'm going to get PbNO3 2. Anything with nitrates are also soluble, so I'll label that as aqueous. Now considering the do-si-do as we start predicting our products. Potassium is going to hook up with nitrate, and we'll do the lead with the carbonate. So our first product, we got a +1 and a -1. So one of our products will be KNO3. We got group 1 cations and nitrate, so I know that that's soluble or aqueous. And then the lead with the carbonate +2 and -2. And that's going to be a solid because it contains lead. Alrighty, let me start putting all these pieces together in my complete molecular equation. Leave room for coefficients. We're going to have to balance it. So potassium carbonate, aqueous, plus lead nitrate, also aqueous, are combined to form solid lead carbonate, lead 2 carbonate, and potassium nitrate, which will be aqueous. There's 2 for my potassium, so I'll throw 2 out front of the potassium nitrate on that side. 2 nitrates, 1 carbonate, 1 lead. Good to go. Complete ionic equation. I'm going to break up everything that's aqueous. This 2 means that there's 2 potassiums, so I'll bring it out front. You got to keep on labeling everything as aqueous if you're breaking it apart. The 2 goes back to the lead, that's the charge on the lead. And then it also tells me that there's 2 nitrates per every 1 lead floating around in that beaker. On the product side, I have a solid. And then I'm going to distribute this 2 to both potassium ion and the nitrate ion. My spectators are potassium and nitrate. So our net ionic equation then will just be carbonate plus lead forming lead carbonate. Here we have copper 2 nitrate with magnesium sulfide. So for copper 2, I know that that's going to be Cu2 plus and NO3 minus. The reagent then, after I do the crisscross, will be CuNO3 2, and I know that that will be aqueous due to the nitrate ions. Magnesium's in group 2, so I'll do a 2 plus. Sulfide comes from sulfur, that's in group 6A. Plus 2 and minus 2, it's going to be a 1-to-1 magnesium sulfide, which will also be aqueous. In terms of our products, copper will combine with sulfur, and we need to consider the combination of nitrate and magnesium. So with the copper and the sulfide, we have a 2 plus and a 2 minus. So it's a 1-to-1, and that's actually going to be a solid. Most sulfides are solids with the exception of whenever they combine with group 1A or 2A ions. The other one is going to be the magnesium nitrate. I have to rewrite that, but nitrates are always soluble. Rewrite it, reorder it. Magnesium first, nitrate second. And I'll crisscross down the 2 to give me MgNO3 2, and that's going to be aqueous. Putting this all together in our complete molecular equation, I have CuNO3 2 aqueous plus Mgs aqueous, magnesium sulfide, goes to form copper sulfide, which is a solid, and aqueous magnesium nitrate. There's 2 nitrates over there, there's 2 nitrates over here. Ooh, it's already balanced. So all the coefficients on this one are all 1s. Moving on then to our complete ionic equation. We're going to break down everything that's aqueous. I'm going to have Cu2 plus aqueous. The 2 tells me that there's 2 nitrates. One magnesium ion, 1 sulfide ion, copper sulfide on my product side, one magnesium ion from the magnesium nitrate. And then I'll bring this 2 out front. So I'll have 2 nitrate ions. Spectators are going to be nitrate, and it looks like our other spectator is magnesium. So I'm going to eliminate those. I'm not going to rewrite them in the net ionic equation. Therefore, all that I'm left with is copper 2 plus, the sulfide ion, and on the product side, the solid copper sulfide.